Hello, welcome back to our CSCI 430 operating system. And for today's chapters, we were going to move on like new topics and more like deeper talk about what's the processes and threads. Okay, so what's the distinction between what's the process? And then when we heard a lot about like threads, okay, so what the distinction or the relationship between them, also what the properties of the threads. Okay, so here's we're going to cover for today's lecture. And in the operating system, there's like called the internals and design principle. Just remember the basic idea is that the several components in any like complex system will perform particular subfunctions. So that they contribute to the overall function. So here's the things that in any complex system, in any system. So how can we perform a particular like subfunctions? So when we think about subfunctions, okay, how can we match with the processor and then first? So that's what we're going to cover. So right here, when we talk about processes, so we have two characteristics. Okay, so one is the resources ownership. So when we talk about a process, so it should include like virtual address space to hold the process image. So this one we need to recall what we talk about. Okay, the PCB or memory, that part. So if you remember, we do have the process image. If you remember what we covered, the OS performs the protection function. So here's one of the features like function that the OS provide. If you remember, we have to do the protection. So to prevent unwanted interference. Okay, so between the processes with the respect to resources. So this one is called like the resources ownership. Another one we we cover talk about details is about the scheduling and execution. So it follows an execution path. So it may be like interleave like with other processes. Okay, a process, if we say it has an execution stage. If we remember, we have like 5 stage. Okay, so start from like new, ready, like running. Okay, so all this stage, and then at dispatching. Okay, so also we have the dispatch, right? So before we execute running, so we need to dispatch it. And if you remember, we have the graph like showing the let's say we have the process A, B, C, D, right? So we need to let dispatch the process, and then we need to execute it. So here's the dispatching priority. So it's like scheduled and dispatched by the OS. So here's the two main characteristics right here. And the units when we like talk about dispatching is referred to like as a thread, okay, or the lightweight process. So when we talk about lightweight, so it kind of like we talk about like subfunction somehow, so you can kind of say that first. So the unit of resources ownership is like refer to as a like process or a task. So now if we mention like process or like we have tasks, so it actually represents the same thing. Okay, it's a process. And when we saying the units are dispatch, so it will be the thread. Okay, when we talk about multi-threading, if you remember we our like previous lectures, we talk about the multi-threading, right? So it's the ability of an OS to support multiple concurrent. So it's like concurrent path of execution within a single process. So when we say like multi-threading, so it should be like saying it's the execution within a single process. So we need to like be careful of this part. So right here, if we say the single thread approach, so if we here we look at in this part, when we have a single thread of execution, so per process, so in which there is kind of that concept that thread is the non-recognized. So is they also refers a single thread approach. Okay, so one process, one thread. Okay, so actually it means the same. If we have the one process and multiple threads right here, okay, one process and multiple threads when you allow. Well, we have the multiple process, and then also they have only like one thread per process. Okay, here's the things. And also we have the like multiple process and multiple threads per process right here. And MS-DOS, when we talk about the history of OS, so it's an example like early system, like one process and one thread. That means that I execute as a whole part, so one third, okay? So when we try to apply on it, so when we talk about in this like figure, the white half right here, so it's like depends the multi-thread approach. So we're going to do, and also the Java runtime environment also is an example of a system like one process and with multiple threads. So here's the idea. How would I try to doing the classification when we look at it? If we have the like let's say there's a address space when we address space one process and then how many threads that per that one. So maybe the early like mesh tools or like the MS-DOS that one. So only one process, one thread. Okay. Later we have some like embedded when we talk about the Java. Okay. So this one we talking like we have one process and many threads. Okay. So when we move on for the latest one, we have multiple processes, but those only have one thread. Then that means that all of them we support multiple programming. You might be thinking when we talk about this one, thinking yeah, it should be pretty common, but with the long day in the like early stage, so it's like we try to handle one process one by one. But right now we can handle like multiple, but only they like have only one thread. So you can still count it as just like one process and only one thread. That means we are still handling this process only. Okay, is a traditional Unix. Okay, but like one is nowadays should be multiple process. That means we have so many processes, and then for this process, one process we have multiple threads. Okay, so here's the ideal design. So in view OS, we should like have either one or many address space. Okay, and that means we have more process, and also we have like one or more many threads per address space. So here's the idea. So you need to know. And the process, so when we talk about the unit or the resource allocation, and there's also a unit of protection. So we need to protect the virtual address space that holds the process image, if you remember, like included. And the protected access to maybe the memory. Okay, if you remember where the memory, the files and IO resources. Okay, so this is like what we covered before. And when we talk about one or more threads in a process, okay, so when a thread execution stage, also we can just imagine it because we try to break down the process into multiple threads, and then actually we do have the same like stage. Okay, so those that run ready, okay, all this. Also, we have the context. If you remember, with the process state context, and that means that we also have a saved third context. Okay, but this one is the independent PC. Okay, and also the execution stack. Okay, each thread needs the separate one. Okay, we just apply the same idea, like what the process doing, because just thinking the we break down the process so into multiple threads, right? So actually they also pretty similar characteristics, and all resources and memory share. So you see all these characteristics pretty similar like in the process, because actually it's like kind of like it's another that process. Okay. And in a single thread model, we can like compare with it like first and between process. So for the single thread process model, we have the process control block. Okay, we have the user stack, kernel stack. Okay, if you remember what's the kernel, okay, for OS and user, okay, user program, okay, and user address space. So this one is the single thread. But if we have multi-thread process model, we do still have the PCB, okay, users address space, and each of them, because we're going to break down, we have the thread control block, okay, TCB, and then TCB. So right here we usually we just break them multiple thread, and then each of them they their own users, and then to the kernel stack. So here's the differences. When we look into the one process, so here is compared to multi-thread process. That's how it looks like, okay. And what's the benefit? Because we try to introduce, or maybe if you look at the like the modern OS, okay, because we already apply multi-thread, multi-processes, okay. So the key benefits of a multi threads like derived like from the performance implications of sharing resources, because we can take less time to create threads than process, and we have a less time to terminate, okay. And kind of like we're giving the less time to switch between the two things. Okay. Everything just like the minor copy, a small copy of a process. Okay. So once we're going to execute, so we can like it takes less time to create. because we have a one process. Okay, if we need to load into it, or like we just imagine, okay, this is one process and one single thread. Okay, we have to execute all them. But for multiple thread, and then we can execute this one. Okay, and then the next one and this one. So we can like support less time to create, less time to terminate, also less time to switch between them. So here's the everything we can enhance the efficiency and share memory communication. That's so what we're going to do. And at first, we're using a single user system. Maybe you just need to know, okay, of course, when we are not really doing in single user, and we have like the foregrounds and background work. Also, it can give a synchronized processing. It also increases the speed of like execution or like modular program structure. So because like when we need to create a threading, so we need to have a modular program structure. So when we keep talking about about the threads, because in an OS, so we need to talk about support other threads. Okay, then the scheduling and dispatching, so it's done on the thread basis. Okay, that's like we need to know. Even okay, so when we learning operating system, or like when we need to execute certain applications, okay, even this computer, okay, the OS support multi-threading, but if the program itself doesn't like return in like multi-threading, that means that it's useless. So that means we need to know even the OS supported threads. Also, we need to let the program itself, okay, also like working in the multi-threading. Then we can doing the scheduling and dispatching, okay, on the like the thread basis. Okay, so suspending a process involves suspending all the threads of the process. We need to know the characteristic, because we are looking into it. If we suspend this process, that means we suspend the process. So it makes sense, right? And also the termination process, that means we terminate all the threads within a process. So it's the same idea. Because this one applied to the stage. If you remember, we have the waiting for event, or sometimes we need to have a suspend state. Okay, so this way suspend or termination. Okay, so all this, because when we look at the process, no matter we terminate or suspend this process, that means that all the threads will be going to be suspended or terminated. Okay, so it's pretty straightforward right here. When we look at the multi-threading applied on the unit processor, so how they going? Let's say we have the threads A, B, and then thread C. So A, B supposedly belongs to process 1, 2. Okay, and then C is belongs to the process 2. Okay, when the time's going, and of course we have the running stage, assuming that T equals to N or somehow, and then we are executing. Once we finish, we do have some like interrupt, we do have IO's request and waiting for request. Okay, well here giving times like called the time quantum expired, because later when we talk about the scheduling, because all the threadings or like for process scheduling, we do like sometimes we give the time quantum like for one process. Okay, and right here, so we will from the invited stage, and then after we finish the thread A, then we will switch to thread 3. Okay, and then maybe we'll go back, and when some in certain time like T equals to N, then the thread C, that means process 2 comes in, have a thread C, then we try to create it, and then start with that like with this stage. And in so far as the moment we finish process 1, that means we finish the thread A and thread B. Okay, we start running the thread C, process 2. So it's how the unit processor doing. Okay, taking time. Okay. And how about we talk about the thread synchronization, this one, because it's the necessary to do the synchronization. Okay, the activities of the various threads. Okay, we need to know all the threads of a process. They share the same address space and other resources. So we need to know, just imagine that they be in one process, and we have like multiple workers right here split. So they're still sharing, like, okay, not this. And in the alteration of a resource by one thread affects other threads in the same process. So it's really important. So you need to be careful of this part. Yeah, because like you are working together, so that's why synchronization is important. Okay. So right here, we will go through all this about the resources, and then just like kind of review about what's the process, and then first just like step back once again, and then what about why the process, and then why like first. Okay, right here we ask the um reason. What's our goal? Because we need to do multi-programming. Like how can we like do it more efficient, right? So we how can we run multiple applications concurrently? So this is what we are asking for. We want to do it. We want to run all multiple applications concurrently. We don't want to waste the time. We don't want to waste it. Okay. And also we want to do a protection because we don't want to have a bad like, application to crash the system. So here's the our final goal, our target. Then how can we do that? So we're going to create like different processes. Okay, so it's a unit of like execution or allocation. We create different processes, and then we try to give in the abstraction. So if you remember, we talked about OS, virtual machine abstraction. We give the process the illusion it owns the machine. Let's say the CPU, memory, IO devices like multi-complex. So that's why if you remember in exercise, we have one resources, two processes like this. Okay, but all these processes they are thinking. We have the virtual machine abstraction, so they are thinking, okay, I own everything. But in actually, it's the OS help us to managing. Okay, then what's the challenge if we want to using this solution? Well, we need to create those processes, and then we need to like switching like those applications. But like it we call expensive, of course, the time that cost all this, so it costs it. And also we need to doing like concurrency like within the same app. Let's say the web server, all this. So it's the part. Then how about we think about we have a process. How can we like making a like the sub function or something like this? So how can we create that first? Okay, decouple allocation and execution. How can we like run multiple threads within same process? That is the idea. So that means that we have the first what was our goal? Okay, then we try to give a solution. Okay, but it causes a problem. This solution is not yet good enough because we're looking at the virtual machine abstraction. Then we say, okay, we still have some certain challenge. How about we put it down? Then we're using the first. So that's why it's really similar. Okay, so we just like break down. So here's the idea. After this, then we try to put it together, all these like process. Right now, it's like in the Unix, we remember we have the process, and then we have the one third thing. So let's say we have the memory stack right here, all the resource IO stage files, sockets, and the context. Remember, we talk about the CPU stage, program counter, okay. Certain like at register all this, and also we have like sequential stream of instruction if you remember like right here in the program. So all this part is a process when you look at it. But when we talk about the processes, okay, so right now we have like process one, two, until the process n, okay, right here. So all this will be same, okay, on the content memory stack, IO, and then CPU stage right here, okay. And all this, like they're thinking they own everything, okay. We have the CPU and then we have a scheduling, but because this time, because we only have one core CPU, just thinking, so every time we only execute one process at a time it causes a problem because we need to switch it. Okay, we need to switch from process one, two, three to n. So what's the overhead? High. But what's the CPU state? Low, because we always need to waiting for switch. And how about the memory IO stage? Because we need to keep switching, right? This part is pretty busy, busy, busy. So that's why high, high. Okay. How about process creation? Because we need to keep on create, so it's high. Protection, CPU, yes. Well, the memory IO, yes. Okay, so if you forgot, we talk about we don't have any like bad application in crash system. So every time we try running process, of course, every time we like switching, loading, of course, we can do protection. But how about sharing overhead? Yes, it's high because in word, right? Let's like context switching, right? Keep on switching. So here's the issue right here. Now, when we go more detail, like the CPU, let's switch from process to process right here. Let's say we have the process P0 and then also P1, okay, and then under the management of operating system, start from execution right here, like certain time, maybe we enter the stage, and then when we have certain like, interrupt or system call, then we need to save the state into the PCB, okay, and then just go down and we will going to maybe have something, do something, then we need to reload the state. Let's say if we're going back to switch process 1, then we need to restore the stage of the PCB1. Okay, we execute. Okay, maybe it also receives the interrupt or system call. Then we need to save the stage of PCB1. And then if we need to go back to process P0, then we need to reload the stage of the PCB0 and go back to switch. So this one is called the context switch. Okay, we know. And the code execute right here in kernel approach they call it overhead. Okay, so it's called overhead because it says a minimum like protocol switching time. So here it keeps switching. So here's the idea. Then because we have the multiple process, so right now we try to implement the multi-threading, right? So all the process we multi-thread right here. Okay, when we're loading and then multi-thread like P1, P2, or like until the PN. Okay, for the switch of overhead, we're getting like the load in only the CPU stage. Okay, this time is that I have like one thread at a time. So also it create the load like thread creation. Okay, and also the protection CPU, but not for the memory. Okay, I because we have so many threads away right here. Also sharing overhead is slow because we the thread switching overhead pretty low. So here's the idea because we like one process and then one multi-thread. Okay. And how about we do have multiple cores? So right now, if we're like talking like one process, okay, one CPU and one process, multiple threads, okay, and then with one CPU. And this time, when we have a multiple CPU, okay, multiple cores, okay, so process 1, 2, and then threads right here, so many threads. And once we the OS when try to scheduling. So we have like 4 threads execute in a time. Okay, because we can assign, because we have 4 courses right here. So it can bring the benefits like first like switch overhead, low thread creation, low protection. Yes, okay, of course on the memory IO because we have more, so it's no. Okay, and then share overhead is low. Okay, so we can compare to here, like because the switching overhead of the each process compared to here and sharing overhead. And then because the using multi-threading, it can bring down lower. And also it can perform better when we have multiple cores. Okay, that means the meanwhile, if we have 4-core CPU and we can handle the 4 threads. Okay, maybe process 1, 2, okay, or I don't know, maybe like 1, 2, 3, 4, and then bringing each one of their friend into it. So it depends. So that's why for the memory or IO maybe still not yet really well protected, but for the protection, but for software creation, switch overhead and sharing overhead will be lower. Okay, so here's the idea. And CPU switch from the front to front. So here switching the context. We call the switch context. If you remember right here, we say, so this one calling the switch context switching. So it's from one thread to another. So in the same process. So it's like that. And also the thread switching also is much cheaper. It's like because it only involves switching the processor stage, the PC and register, because also it's like generally very efficient. If you remember, we talked about the PC where you create a memory. So if you remember the content of it right here, okay. So multi-thread model. So that's why it brings the benefit. Okay, so of it switching. So that's why only the switching the process state. Okay, also that's why it's more like efficient. Kind of like here, so you can so the life cycle of first, or like if you look at the process, because it's kind of like it's a kind of like as a functions, or you think in tree is a process. So we also start from new stage, and then we have a ready. Okay, maybe like we have a schedule like dispatches, so we are running stage. If we finish, we have a terminated stage. Okay, that means we can exit. Or if we in one stage, if we receive some like event waiting, so we're waiting stage, and once it complete, we put it back to ready. So far right here. So it's the same for the for a third to execute. So it's changing all this stage, new, ready, running, waiting, terminate. So right here. And we call it the active threads. They are represented by their TCB. Okay, the thread control board, right? So we have the PCB, process control board, this one because we have the TCB. So they are organized into queues like based on their state. So just need to know one thing. So this is called the active threads. Okay. And so far we will just like have a review questions right here. If you're interested, you can take a look. So right here, So we talk about two separate and independent responsibility of a processor and thread. So we can talk about it. So we say right here context switching, or we say also like maybe the right here between the interrupt. Okay, so all this, and then you can look at the multi-thread environment thing about is a process defense unit for resource allocation, unit of protection, process switching overhead. So it can be like high compared to thread. So is it because if you remember the graph right here, switch overhead, right? And then there's still more question. If you're interested, you can take a look at it. And then for the next part, I'm going to it will be move on about the type of the threads. Okay, so I will meet you in the next video. Thank you.